Okay, let's start with our exercise class today. So today the main topic we'll be discussing are direct and indirect measurements, and the first thing that we're going to discuss is the interaction Hamiltonian. So it's when we have two systems and we want to indirectly measure the first system. And to do so, what we can do, we just can couple it to the second system and then analyze the state of the second system. And this is done by implementing interaction Hamiltonian. So you already seen this in the lecture for when the interaction Hamiltonian was observable tensor product the position on the second system. And in the exercise class case where we take the interaction Hamiltonian, which takes the tensor product with the momentum. So to recap what I said formally, what we have here are two systems, which we call S, which is a system of interest, and P, which is the pointer. So the intuition to consider here is that if you think about the measurements that we perform in the real world, actually, it's very hard to find a measurement which we do directly. So for example, when we measure, I don't know, the length of this table, what we do, we don't just look at the table and say, oh, it's this long. And we take a metric, a meter, and then we just take a meter and extend it from one edge of the table to the other. And that's how we measure the length of the table. So basically what we do, we interact the table with the meter. And here it's the same idea. So basically we have a system of interest that we want to measure. We interact it with another system, which we call the pointer, which can also be understood as, for example, the meter with which we measure the table, and then we analyze the pointer. So we consider the following observable on the system S, which we call AS, which we write in its basis. So it's sum over K, AK, KK on A. And this is observable that we want to measure on A. And we start with these two systems being in a state of a tensor product with each other. So the initial state of two systems, A and P, is the following. So the system A is in superposition of the states of this basis K, where the basis K is the eigenbasis of the observable that we want to measure. And the system P, the pointer, is in some state of psi 0. And what we've seen in the lecture is the following. So suppose that we now expand the state of the pointer in a position basis. Sorry, in a momentum basis. So the state of the system A stays as it is. And here we have the integral over P, psi 0 bar P, P on the pointer. Sorry. Yes. Thanks. Yeah, this is all system S. Sorry. Thanks a lot. And then in the lecture, what we've seen is if we take the Hamiltonian H on both systems, S and P, which is equal to AS tensor product position X on a pointer of a pointer, and then we evolve for time t the system under this Hamiltonian. So basically this means that we implement the evolution, which is described by unitary USP, which is in terms of Hamiltonian can be written as e to the power minus I t over h bar Hamiltonian on the systems S and P. So then if we apply this unitary to our state, psi 0 on systems S and P, then what we get out is sum over k, ck, k on system S, tensor product, integral over p, psi bar of p plus t ak, momentum state on a pointer. So basically what happens during this evolution, each of these basis states k, which is in this superposition, gets coupled with the shifted momentum function of the pointer. So as you see, like the difference here is that here we have the state tensor product with this and they're separate, and here we have the sum over k, the tensor products between the kth state in the system S and then the shifted momentum function. So basically for each state k, we have coupling with the momentum function, which is shifted by delta pk, which is t ak, where ak's correspond to the eigenvalues of the observable. Okay, so now this was in the lecture. So yeah, I already wrote this on the lecture. Now we're gonna again walk through the same process, but we're gonna analyze a different Hamiltonian. So here we consider the Hamiltonian HSP, which was the tensor product of the observable A on the system S and the position of the pointer. Now, if we do, we consider the Hamiltonian HSP, which will be which will be A on the system S, tensor product of momentum on pointer. So by the analogy here, you can already kind of make a guess that we will get something similar, but while there we couple to the shift in the momentum, here we would couple in the shift in the position. And so basically what we're going to do now, we're just going to go again through the steps that went in the lecture, and yeah, please slow me down and ask questions if any step is not clear. So the first thing that we have to write out is so maybe the first thing before we actually write the unitary under which the state evolves is we write the joint state. Again, just to repeat, so again we have the initial state of on the system S, which is sum over k, ck, k on S. Tensor product, the initial state of the pointer, psi 0 on the pointer. And this state evolves to some psi tilde of SP, and it evolves under this Hamiltonian, and we can write the evolution using the unitary USP, which is e to the power minus I t over h bar r Hamiltonian. So the first task for us is to write out this unitary, how it looks like, and then subsequently write the final state of the systems S and P. Okay, so let us analyze this unitary. So this is the e to the power minus IT for H. HSP is a S tensor product momentum of the point. So since this is a operator exponential, one thing we can do, yes.
Remember where along actually first the unit that E, these two are equivalent, but why? I mean, but the question is more, what if I wanted to have a different unitary? What I'm seeing is unitary is basically bound to the Hamiltonian. The Hamiltonian is basically given for a system.
Yes.
For something different, I can't do that.
So suppose that you have a system, right? And then you have you know that the system is governed by the particular Hamiltonian. Then according to the Schrödinger equation, the evolution will always be given by this exponential for this particular Hamiltonian. Of course, you can vary the Hamiltonian, but given the Hamiltonian, this is how you write the evolution, basically. Does it make sense?
Yeah.
Okay. Okay, so we see the matrix, the operator exponential. What we can do is, just to write it out more clearly, we can write it as a series, because every exponent we can write as series. So this is sum from 0 to infinity, minus IT over h bar to the power n, AS tensor product BP to the power n. Because this is a tensor product, which is to the power n, we can just write it as the tensor product of the corresponding powers of n of the particular of these operators. So this is the sum from, and I of course forgot the 1 over n factorial. All right, yeah. So power n, AS to the power n, tensor product P to the power n. So then now let us consider AS to the power n. So what is this object AS to the power n? So AS is this observable, which is written in its own eigenbasis. So we can write it as sum over k, ak, kk on the system S. Of course, one easy way to see how we put it to the power n is to just consider, for example, consider the matrix which corresponds to this sum, see that it's a diagonal matrix, and whenever we multiply diagonal matrices, what we get is always a diagonal matrix. Another way is to consider it inductively. So for example, let us first consider AS squared. So AS squared would be sum over k, ak, kk, multiplied by sum over, let's say, k prime, a k prime, k prime, k prime. Then what we will get here is the sum over k prime, ak prime, k. Then we'll have brackets of k prime, and the bra of k prime. And this will give us the Kronecker delta. So it's delta k prime, which means that this is non-zero only for the terms where k equals k prime, which means that this is the sum over k, ak squared, k. And then by induction, we can see that as to the power n would be sum over k, ak to the power n, ak on the system S. Okay, so we got this representation of the operator as to the power n. So now let us plug this in here. So we're going to have the sum power n. Here we'll have sum over k, ak to the power n, k on S, tensor product, p on p to the power n. Okay, so now let us massage this equation a bit. So we're going to do now, we're going to exchange the order of summation between k and n. And just write this as a tensor product of sum over kk and the exponential of the momentum operator. So we're continuing our thing there. So write US E of t equals sum over k k on S, tensor product sum over n, minus IT, we can input AK here over H bar to the power n, P on P to the power n. And this is just another matrix, so operator exponential. Yes.
1 divided by n.
I just forgot about it. Yeah. But sorry, thanks. Yes, so basically what we arrived to is that we can write our unitary as the following. On S, tensor product by e to the power minus IT AK over H bar momentum on P. Okay, now the last step is we apply this unitary to our initial state. So to this state. So what we get is, let's in our unitary, instead of K, write K prime, because in the initial state we already have summation over K and we don't want to mix that. So we apply sum over K prime, K prime, K prime on S, tensor product e to the power minus IT AK over H bar P. And this we apply to sum over K, CK, K on S, tensor product, just psi 0 on P. So what we get, we just apply each of these separately. So when we apply sum over K prime to CKK, K prime and K, the bracket will give us the delta. So the only terms that will survive are those for which K prime equals K, which means that we just will have one sum over K, CK, K on S. And this is going to be tensor producted with just applying this exponential to the psi 0. Minus I, TAK over H bar, P on P, acting on psi 0 on the pointer. So this is the result of applying our unitary. Let's remember this. So here we already see that we're observing the same effect, essentially, that each of the states K on the system S is coupled with the operator which depends on K acting on the state of pointer. Yes.
Summation on the left-hand side is different from this product. On the right-hand side, we have AK. So the tensor product on the left for the second, we also have AK, but we sum over K prime. Right?
Yes. Okay. This is a good point. This is K prime.
Sure, but I mean, on the right-hand side, we already have K on the right of the equation. So the solution is K. My question is, what this that Lídia delta magic is happening on the left-hand side, not on the right-hand side. So,
okay, so this is like, you see this object, right? And so, and we have here two sums, and I can just bring this sum in front here, right? And then just and then I have sum over K prime, sum over K, and then this object acting on this object here. Because it's a tensor product on both sides, then I can just consider this is equal to this part acting on this part, tensor product, this part acting on this part. Okay, and when we act with this part on this part, we see that the only terms that survive are where K equals K prime, which means that whatever happens on this side, when K is not equal K prime, what we get is a tensor product of 0 and something. And this is 0.
What is that?
We're gonna consider it a bit in a bit, yes. But as again, like taking the analogy from the lecture, we've seen that the same thing with when we have the position here gives us the shift in momentum. So because we have this kind of correspondence between x and p, then one can guess that if we exchange x for p in this exponential, then we will get shift in position. But yeah, we're gonna come to it now, basically. Okay, so indeed, let us just take write this down in our memory, and now we will just consider how this operator acts on the wave function. So let us take an operator which is e to the power minus I L P over H bar, and let's see how it acts on some wave function psi. So basically, when we will calculate this, we'll just substitute L by TAK and we'll get our result. So this operator, by the way, it's also called modular momentum. And one thing that you can already see is that in which basis it's easier to consider this kind of operators. So for example, if you have a function which is a function of an operator p, it's always easier to analyze this function in the momentum basis because there it acts trivially. When you see the function which is a function of x, then it's always easier to use the position basis because there it acts trivially. So by acting trivially, what I mean is that if we take this modular momentum, then and act on it on the momentum function, it would map psi bar of p to e to the power minus LP over h psi bar of p, where here p is just, it's not an operator anymore, it's a variable. So why does this happen? So suppose that we act with this operator on this state psi, and then we want to see what is the momentum representation of this. So the first thing to see here is that if we act with, if we act on the right, on the bra p with this operator, what do we get? Can somebody tell me? Yes.
You could technically expand the exponential and then you
Yes.
have to p
Yes.
raised to the power of n.
Yes.
And because the basis of p is p,
Yes.
so you just get the momentum out and then you contract that summation again and you get an exponential without the operator, but just not.
Yes, exactly. Very good. So basically what we get, so your strategy is exactly correct. We see this exponential, we expand it as a series, then we get like a bunch of p to the power n acting on the bra p. And basically because we know that p just gets us the eigenvalue p, then all these p's come out, and then we contract the series again, and it gives us the exponential with just the value of p. Is this more or less clear? Yes. So yeah, so this is the operator which as the eigen basis has the momentum basis. So p acting on p will give us just the value of p. So this is the operator. And this is the eigenvalue. So it's just a yeah, it's just a number basically. Okay, so then we can write that this is actually e to the power minus LP over h bar p psi. And this is just psi bar of p, just our momentum representation. And the same logic applies to like any function of the operator that you would have here. Because I mean, first, of course, we have the assumption that all the functions that we consider are nice, so they're kind of expandable in terms of the series of the powers of this operator. But given that can exist as the series of p, you can always conclude that we just get out the value of that function at the point p. Where? Yes. Oh.
The p there is square root.
Oh, where's square?
The p.
Why?
The exponential because you apply p squared.
We don't apply p squared. It's LP.
That's just p. It's a p.
It's just a p, yeah.
Ah, okay. Yes. So that was the question.
Ah, okay. No. So this is not the like p squared over 2m Hamiltonian. It's just the modular momentum. So when we have some number which is multiplied by p in the exponential.
Yes. So you.
Ah, sorry. Okay, so now we know how it acts on the momentum representation. And also we know the trick how to go from the momentum representation into the position representation, which is the Fourier transform. So this is what we're going to do. So while I'm raising the board, if you're feeling like it, you can already start calculating how this modular momentum acts on the position representation. Which is very easy because we know how it acts on the momentum representation, which means that we just have to take the result of the application to the momentum representation and apply Fourier transform. Okay, so what we know is e to the power minus L P over h bar maps psi bar of P to e to the power minus I LP over h bar psi bar of P. Now our question is, what if we take psi of x? And the answer is Fourier transform of this. Okay, then let us start calculating this. So we just apply Fourier transform. So 1 over 2 pi h bar integral over p e to the power minus I LP over h bar psi bar of p e to the power I xp over h bar. Okay. Let us join to Yes.
We define a metric as coupled with our system evolving over time, and then the conclusion of this metric will have coefficients.
Yes. So, but it's both systems that evolve in time.
Exactly. So
Yes.
what did the metric give us at the end?
The matrix, the joint matrix.
Not the metric. It's that we have a point here. Measures the system parallel.
I'm afraid I don't quite get your question. So in the end, as a final state, we get a superposition of the tensor products of the state K's on the system with this transform state of the pointer. And what we're doing now, we're trying to see to what physically this transform state of the pointer corresponds to. So say that so if I measure the pointer in the position basis, what would I get? So basically, so for example, if you have this joint state, right? If you measure the pointer in the state which corresponds to this transform state, which is basically shifted position, but we're just getting there. Then that already tells you in which state the system is. Yes, so it's the same. It like classically you can see the following analogy. So for example, you measure the length or the voltage on the system. Yeah, I guess length is a bit harder to see because it's something that we can see with our own eyes. But for example, you measure the current or the voltage, and then basically what you have in hands is your meter, right? So it's and then you look at the pointer of the meter, and then by that you gauge the result. It's just that here in quantum mechanics, the act of looking at the pointer corresponds to the measurement, which is explicit. Does this make sense?
Yes. Your question is why is one system
so the observable that we choose on the system in this case is SQuID. So in principle, the same procedure would work for a continuous observable as well. So I mean, so for example, discrete. I mean, because some observables that we can consider are discrete. For example, the spin of the system. So we want to measure the spin of the system, and we couple it to the shift in position, for example. And this is basically what happens in the Stern-Geller experiment. Yes. Okay, what I can do is I can write more solutions with more explanatory paragraphs. Would that work?
I mean, sure. I just don't want to write during exercise session.
Okay. Okay. Yeah, I'll see what I can do. Like I have some notes which are handwritten, but I can in principle rewrite them on the iPad and then post them. Okay, or I can just scan them and yeah. Okay. Okay. Yeah, if there are no more questions, there is just one last step that we have to do, which is to join these two exponentials, which are just crying to be joined together. So what we get here is e to the power IP over h bar x minus L. Okay. What is this? This is by definition is psi of x minus L. So what we get is that this modular momentum operator maps psi of x to psi of x minus L. Great. Now our theoretical considerations of this modular operator to the position wave function are concluded, and we can apply our newfound knowledge to our state there. So we have the state sum over k, ck, k on s, tensor product with e to the power minus it ak over h bar p on p acting on psi 0 of p. So let us write psi 0 in the position basis. What we get is integral over dx psi 0 of x. And we know that when we apply this operator to the position representation, what we get out is the position wave function, which is shifted by the corresponding coefficient in the exponential. So there it was L. In this case, it's TAK. So basically what we get here is sum over k, ck, k on s, tensor product, integral over x, psi 0 of x minus tak x on p. So in the end, we come to a somewhat similar conclusion as in the lecture, but here we see that in this case, we couple the states k on the system S to the shifts in the position. Okay. Yeah, I think we can make a break now. Are there any questions? Please ask.
Let's just It's a small presentation. Once we decided
Oh, you need to
YouTube. Oh boy. Oh boy. Oh. Those are the tools that well, this didn't remind me. Yeah, like should have posted or something. Honestly, I don't waste the time day. Can't answer.
This kind of surprise me. They like that. No, they don't, or not, they just do it. Last year, this sports.
So
Yeah, exactly.
yeah. It's obviously working out. You're like 4 pages, so you're like, okay, great.
Yeah, but like I think this happened last year. Jason and I presentation class.
So, you know,
People enjoy it.
just look at this. My slide is just so it is. Because all of them are good.
And then what did you get home?
Any long, well, okay.
Yeah, not that bad. Like I would expect that, like, who expect this is interesting, and some people really have sort of thing to read, like, read.
So again, a question on the
Oh,
interaction.
sorry, let me wear the mask just in case. Yeah.
A question on the interaction of the metric with the system. So by measuring something, we interact with the quantum system, first need to change.
Yes.
We incorporate this in the Hamiltonian, which we make as a tensor product
Yes.
of the observable times position thing, and we measure some of the, in our measurement. We have a particle which has some discrete properties and some continuous properties. Plus, if we only measure discrete properties, we don't, or observable doesn't interact with continuous properties.
Okay. Oh, good question. So when we write something as a Hilbert space, this Hilbert space corresponds to a particular degree of freedom of the particle. It does not. We do not strive to describe the whole particle, but we for example want to describe its spin, and then for its spin we have the Hilbert space, which is discrete, two-level, so on. If we want to additionally describe its continuous degrees of freedom, then we tensor product is.
But the question is, now what we're trying to mimic here is, instead of making it observable and saying it collapses into the state,
Yes.
we're trying to incorporate this collapse in the observation by changing the Hamiltonian.
So we want to implement, we want to be able to not measure this particular property, but measure other property and then infer the first property from the second. So for example, spin, right? We cannot measure the spin directly.
Yes.
But what we can measure is the position of the particle on the screen.
Yes.
So what we do, we send the particle through the magnetic field, which is basically coupling their like y position, let's say, with the spin, and then after going through this interaction, it just goes into two different directions. Yes.
Exactly. And then the question is, why does our interaction Hamiltonian interact with the spin at all?
Interaction Hamiltonian. This is something that we can. This is something that is given by the lab, basically.
We took the Hamiltonian.
Yes.
How does it correlate with the observable work? So our Hamiltonian is of the form AK times PK.
Yes.
And the observable is AK. Why is AK in the Hamiltonian and not? Why would it be? Why do we put observable in the Hamiltonian?
This is a choice because we want to measure that observable. So basically, this is a choice because we want to, because suppose that you take something else but not AK in the Hamiltonian.
Identity.
Yeah, identity, let's say. Then basically what you would get is, yeah, you will just get the initial state of the system, tensor product with its separate evolution. So it's not going to couple the terms in the initial state to the state on the second system.
Technically speaking, in real measurements, we wouldn't take observable. In the Hamiltonian, we would take something similar to the observable, so that we can.
No, I mean we can take the observer. For example, in Nurgalieva, right? We know that the spin interacts with the magnetic field in a particular way, right? So then, by implementing. Why not? The spin.
Because then it's a property.
Property and observable are basically the same.
But like one thinks of observable is measuring a property, or
observable is a property. Measuring a property is a process. So, like quantum theory in that sense is very operational. So you have particular things you can measure, and then you have the measurement process. And in this case, we model the measurement process as this unitary. But then when we actually measure, then we measure in a particular basis and we collapse the states.
Unitary is a measurement process.
Yes. So we're getting close to the measurement problem, don't we? So, I mean, I guess like discrete case, which is easy to see, if you remember the qubits, then you have, for example, this plus state here on the first qubit, and then you have a state 0 on the second. And then you apply a CNOT gate. And this can be seen as measurement from the outside, because what it does, if we look at this qubit as memory, it basically copies the state into the memory. It's a coherent copy. So in this case, like the memory and the system are correlated. This means that if we measure 0 here on the second qubit, like let's say we do the measurement, we know that if we would have measured the first system, we would also get 0.
Yes. Yes.
And the same thing there. Yeah.
Yeah. I understand that we have a complement between position and observable property. That's the point.
Yes.
My question was just like, if you can just straightforwardly take an observable and put it into the Hamiltonian.
So I have no idea how it's implemented in the lab. So, but as a thumb rule, theoreticians, we say, okay, we write this Hamiltonian, and then we implement the Hamiltonian. and we know that this Hamiltonian would lead to this noise coupling. How it's implemented in the lab? Good question.
Because I was thinking like with magnetic field, you probably don't get the exact spin-up rule, you get it weighted maybe in some sense.
No. I mean, so the thing is that, I mean, with the Stern-Gerlach, it's clear like one goes up, the other goes down.
Yes.
And
But Hamiltonian is not just a cross product of spin times position, right? In real life.
no, it is. It is. I mean, you can have some additional terms, or whatever, like quadrupole momentum. I don't know, but in the end, you would are two blobs, and then the relative intensity of those blobs will tell you, like the terms in the superposition. Yeah. I mean, of course, there is an option which we're going to consider, but now that when these two blobs are intersecting, like if you put the screen too close, then of course, like measuring the intensity becomes more difficult. But you can still extract some information. Yeah. Okay, this is also true. Yes.
Yeah, exactly. So, yeah. Right. If you're playing this, sure, like the order. Pretty good. Should be good. There needs to be a reason for that to exist. Yeah, well, I say. That might be. Yeah. Yeah. And then first. Yeah.
Okay, shall I continue? So maybe also as an example to continue this line of thought of coupling. So here we couple to the continuous degrees of freedom. One can also couple to discrete degrees of freedom. Like for example, a simple example you already seen in the course, which is the C0 gate. So suppose that I have one qubit, which is S, ds system S, which is in the state. And then I have a second qubit, actually in the 0, which serves as a pointer. And then I apply the C0 gate. Which state I will get as a final state of both these two systems? Good question, right? So I apply the C0 to the tensor products of okay, so how does the C0 act? So if the state is 0, 0, what does it map it to? Yes?
0, 0.
Yes. And if the state is 1, 0, yeah. Yes, exactly. So again, simple rule. So this is a gate which is controlled on the first qubit. So if the first qubit is in a state 0, nothing happens on the second qubit. If the first qubit is in a state 1, we apply the flip operation on the second qubit. So the X gate, basically. So then this is mapped to alpha 0 on S0 on P plus beta 1 on S, 1 on P. So here we see that, again, it's the same scheme as the state above there. So we have the sum over the initial. So in this case, it's alpha 0 and beta 1. And each of these terms is in a product with the different states of the pointer. And in this case, we see that the states of the system are coupled to the orthogonal states of the pointer, which means that, for example, if I measure the pointer and I get 1, then I know that the system S is in 1. Okay, now let us get back to our continuous case. And maybe as an exercise, if somebody's interested, is so here we directly apply the C0 as a unitary, right? But we know that to each unitary, we can find a corresponding Hamiltonian, a corresponding interaction Hamiltonian, which would implement this unitary. So as a side exercise, you can also try to find this Hamiltonian or one of these Hamiltonians because they're not unique for the C0 gate. Okay, so now let us come back to our initial consideration. So let us consider the observable AS, which is A00 S minus A11 S. So now we just consider the simple example of the calculation that we have carried out in the first part, but for when the system S is a qubit. And then we are looking at this observable. Okay, then we know that we apply this Hamiltonian, which is AS tensor product P. And get in the end is the following state. So again, this is equal to the unitary. Let's say the initial state of the S is alpha 0 plus beta 1. And we have the initial state on the pointer. I don't know why I'm wearing the mask. Okay. And we already know how this will end. So what we will end up with is alpha 0 on S, tensor product e to the power minus AI AP over H bar psi 0 plus beta 1 tensor product e to the power IAP over H bar psi 0 on P. So what I did here is just use that formula, or the formula with where we don't consider the shift in the position yet, for the case where C0 is alpha, C1 is beta, A0 is A, and A1 is minus A. Okay, so yes. This is just an observable we can choose. In particular, actually, if you look at it, it's a multiple of the Z operator. So the Z operator is this matrix, right? And here what we have is just the AZ. So yeah, so in this sense, it's kind of a legit operator, but in a sense, you can see its physical meaning right away. Okay, do I have space? I still have space. Okay, so let us call this psi L, because what does this correspond to? This corresponds to, in a position of representation, to psi of x minus, yeah, maybe I also need to add t here. I think I do. T, x minus at. And this I will call psi r. So this is both on the pointer, because in the position representation, this corresponds to shifted position by x plus at. So basically what we have here is the sum of two terms. The first one is the 0 in the system S, and this left side shifted the point of the pointer function. And here we have the pointer shifted to the right. So in a sense, one can also draw these wave functions as, let's say, psi L and psi R. Yeah, I mean, this is this of x. Okay. So we have this situation, and then let us first consider when these two wave functions of the pointer, which are psi L and psi R, they don't overlap. This means that they're so the product brackets of psi L and psi R is 0. And this exactly corresponds to the graphically to that situation I drew there. There is no overlap between two functions.
So I mean, sure, we're looking at the different bases, but is that the only difference?
Yes, that's the only difference.
So it's the same change, but just bases, or are you actually changing something different?
So mathematically, this is a change in different bases. As physically, you need to measure different observable on the pointer. And in some sense, it's easier to see with a naked eye, for example, change in the position, the change in the momentum. So yeah, so basically here you just couple to the position and then you see the position on the screen. Yeah, you can do the momentum, let's say, yeah, you can just have something that would measure the velocity.
No, but I mean, I thought so in the electric, the change in current.
Yes.
But I mean, at the end of the day, so the way I was looking at, for example, if one partial goes straight, and then depending on the speed, it's redirected to that side or the right side, right? You should keep evolving that, or hit a screen at a different position.
This is if it's coupled to the position.
So because I thought that's what we did. Like, what do we do that in effect? Is that describe that?
Yeah, I guess you would just look at the time at which the particle would pass somewhere, and then by that gauge which momentum it had. Like, yeah, I am not sure exactly like how you would implement this. But basically your particle would be still going straight. It's just it would be in a superposition of momentum. Okay, so the first case when psi L and psi R don't have overlap or they're orthogonal. And let me just rewrite the state that we have there. So we have alpha 0 S psi L on P plus beta 1 on S psi R on P. And suppose that we want to measure the pointer. Can you tell me one advantage of this and one disadvantage of this? Or like whatever comes to your mind first. So what is good about the measurement when we measure the pointer in the case where psi L is orthogonal to psi R? Yes.
Where the spin, like so what the spin was, because if the two overlap, that means that something could have come from the spin 0 or spin of 1, right?
Yes. So basically, by measuring by measuring psi L on the pointer, you would ensure that you would have measured 0 on the system. So the system, moreover, has collapsed in the state 0 after you measure the pointer in the psi L state. However, there is one disadvantage which is exactly connected to the same fact. Yes. Yeah, please.
I guess because the system is now basically has collapsed.
Yeah.
State we lost all the other information.
Yes, exactly. So this is a very important point. So when you measure the pointer in the spaces, which is orthogonal to each other, so or you even construct the Hamiltonian in such a way that these two are orthogonal to each other, then after you measure the pointer, you lose all the information about the initial state, because after you measure the pointer, you collapse the state. So if you measure psi L, then the state collapses to 0. If you measure psi R, the state collapses to 1. So even though this measurement procedure gives us kind of exact correlation between two systems, it is in some sense not optimal, because we lose the state we started with. And that's why this measurement is called a strong measurement. So because it affects the system in the strongest way possible. And so there is a way out of this, which becomes evident if you look at how the state looks like. So basically what we have here is like some of these two terms. And one can imagine that if the terms psi L and psi R are close to each other, so basically psi L, psi R, say, is like some epsilon, and the epsilon can be, so it's epsilon, of course, smaller than 1, but not exactly 1, then even though the states of the measured system are not perfectly correlated in the sense with these two states, psi L and psi R, so for example, graphically this can be seen that, say, it's psi L, this is psi R. There is this overlap. So for example, yeah, like here. We're still able to extract some information about the system. And this is exactly this case. So this is epsilon, and this is a weak measurement. This corresponds to the case of the weak measurement. Okay. So basically for this, we need to take the overlap between functions psi L and psi R such that it's bigger than 0, but it's less than 1. Because if it's exactly 1, then it's basically the same state up to a phase, and then we can just take this state out, this state of pointer out, and just get a state which is up to phase the initial state. So there is no correlation at all. So and the idea, as I already said, of the weak measurement is that even though you correlate the states of the system with overlapping states of the pointer, and we don't get the full information about the system in the limit of one measurement, then but still we manage to not disturb the state as much as we would disturb it in the case when we would perform a strong measurement. Okay, what's the time? And in the exercise sheet, you will consider the same situation, and you would need to find a measurement scheme, and you can come up with your own for the strong measurement case. Sorry, just let me open. For the strong measurement case, when we perform the measurement on a system P alone, and so basically, we just need to find the following system of projectors when we don't apply anything on system S, and then apply projector P0 on P and pi1 on P. And it should be such that we would get the same statistics as if we would measure the system S in a 0-1 basis. So basically what we would have is the probability of measuring the first projector on system P on the final state after interaction, which is psi SP, is the same as probability of measuring 0 on the initial state of the system system S. Did I name it somehow? So let's say that initial state on the system S is phi 0 on S, which is alpha 0 plus beta 1. And so we measure this on the initial state of the system S. And also the probability of measuring the second projector, phi 1p, and the final state would be equal to the probability of measuring 1 on the initial state of the system S. So the probability statistics would be the same. And additionally, we would have the following constraint, which would make your life a bit more difficult, which is that the post-measurement state on the system S should be the same in both cases. So in the case where we measure pi 0, and in the case we measure pi 1, it should be the same. So for example, if you take the measurement, if you measure just psi L and psi R, yes.
This first time you wrote down these two projectors.
Yes.
Why? The way we did it, I understand it is differently than the one we had until now. So I'm not exactly sure. What are we doing? What is it, for example? What is the P inside the projector 0P?
Here.
Yeah.
So P is Lydia. Did you have like projectors already, or not?
Yeah, I didn't have projectors. No, but what's the P? I don't know. Like, where does the P come from?
Oh, so pi just corresponds to the.
No, pi. P, the subscript. In the pi.
Ah, that's the pointer.
No, on the pi. Sorry, yeah, the pi.
I mean, it just means that I apply pi 0 is on the system P, and pi 1 is on the system P, because now when we write the operators, we always specify on which system the operator acts on.
So it's similar to what we did here, but instead of looking at the discrete as like the continuous case, we won't look at two discrete.
So I mean, so here, basically the pointer is continuous, but in the end, what we get is that the 0 state is coupled to the psi L, and the 1 state is coupled to psi R. So you can in principle come and say that, oh, I would write my projector in terms of this psi L and psi R. Does it make sense?
It's fine. But I just don't understand what the meaning is of first line you wrote there. I just don't understand.
This one.
So you're defining that on the left side. No, defining for like the early braces.
Yeah.
So yeah, I see that you're defining two things. Like one is on the spin is unaffected, and the right one is projected to 0T.
Yes.
So then why? Where does it come from? And how does it have to do with anything else?
So here, what I'm trying to do is I'm trying to find the measurement on the pointer, and when we write the projectors, they always correspond to the measurement. And what I'm trying to do is I'm finding a measurement on the projector which would give me the same statistics as the measurement on the system alone. Yes, exactly. You need to come up with this, which would satisfy these three things. And for example, one can already consider, oh, what if I take pi 0 psi L, let's say, and pi 1 psi R. This would give you indeed the same statistics, but it wouldn't satisfy this third condition.
Why would it work? It's a strong measurement.
So because basically what happens is, what is the probability of measuring psi L here? Alpha squared, right? Alpha modular squared, yeah. What is the probability of measuring 0 here? Exactly. Same for psi R. What is the probability here? Modulus beta squared, right? What is the probability of measuring 1 here? Which means that, okay, the statistics coincide. However, the third condition that the post-measurement state on S in both cases should be the same is not satisfied, because when we measure psi L, we collapse it to 0. We measure psi R, we collapse it to 1. So we collapse them to the orthogonal states. And so yeah, so this is a challenge for you. And also the next thing we would consider is the weak version of this. So this was all in a case where psi L, psi R are orthogonal. So what happens in the weak case? So in the weak case, we have that psi L, psi R modulus, say, is like epsilon. Whichever measurement you come up with here, you can also see what happens if the overlap is non-zero. What happens to the statistics? So you can, for example, calculate what's the modulus of the difference between these two probabilities. So what is the difference between measuring 0, 0 on the initial system, initial state of the system S, minus the probability of making the measurement on the second system, already when these two systems are coupled. So, and how it depends on epsilon, because here, because when you will apply this this projector, you would get terms which are proportional to this overlap, right? And there they would just disappear because of the 0 overlap, but here there would be some epsilon present. Yeah, and you will see how for your measurement, which you would construct, these statistics, how close these two statistics are to each other. I mean, the same for the 1, 1. And then you can also think about what would be the final state of the system after this measurement in the case, in the case where there is 0 overlap, and in the case where it should be the same, and compared to the case where there is non-zero overlap, when the overlap is epsilon. So the question of this measurement state in this case is a challenge. So if you don't solve it, it's fine. Maybe you don't, because for that we actually need the machinery that will be introduced a bit later with the density matrices. But you can still think about it, like how you would write the state in that case. Okay, I think I'm done with everything I wanted to say for today. Please, if there are any questions, feel free.
Some question regarding the collapse in the strong measurement of the collapse system. For every particle to be but we don't know strong measurement which particle rest weird, right? We just know how they distribute, so we should not force the collapse.
So basically, whenever we do the measurement on the pointer, we collapse the system S in a particular state. The question is whether this state is close to the initial one, or if it's drastically different. I mean, in the case like here, for example, you just measure different positions, right, on the screen. And then depending on the strength of the interaction, then this shift in the positions can be far away from each other, which would correspond to the strong measurement when there is almost 0 overlap, or it would correspond to the weak one where there might be quite large overlap between two. And then, like, by measuring position, you wouldn't know if it was if it corresponded to the function where it shifted by a or minus a, if these two are too close to each other.